Carbon capture, exploring technology to reduce global carbon emissions. Agenda: Introduction to carbon capture, technologies and methods of carbon capture, storage and utilization of captured carbon, economic, environmental, and policy considerations, future prospects and innovations. The thesis behind carbon capture. Carbon capture definition. Carbon capture separates CO2 from emission sources or the atmosphere to reduce greenhouse gases. Methods of capture. Chemical, physical, and biological methods are used to capture and store carbon dioxide effectively. Environmental impact. Carbon capture aims to mitigate global warming by reducing atmospheric greenhouse gas levels. Importance in combating climate change. Carbon capture significance. Capturing carbon reduces industrial emissions and helps limit global temperature rise effectively. Negative emissions technologies. Carbon capture supports negative emissions technologies that remove CO2 from the atmosphere. Complementing renewable energy. Carbon capture complements renewable energy by addressing emissions that renewables alone cannot eliminate. Overview of carbon emissions sources. Fossil fuel power plants. Fossil fuel power plants are a primary source of carbon emissions, contributing significantly to global population. Industrial processes. Industrial manufacturing processes release carbon dioxide through chemical reactions and energy use. Transportation. Transportation use in fossil fuels generates substantial carbon emissions from vehicles and airplanes. Deforestation. Deforestation leads to carbon release by reducing trees that absorb CO2 and burning biomass. Technologies and methods of carbon capture. Pre-combustion capture techniques. Concept of pre-combustion capture. Pre-combustion capture removes CO2 from fuel before combustion to reduce emissions effectively. Gasification process. Gasification converts carbon-based fuel into hydrogen-rich gas, enabling easier CO2 separation. Hydrogen-rich fuel. Hydrogen-rich fuel produced is cleaner and supports efficient energy generation with reduced emissions. Efficient carbon separation. Pre-combustion capture enables effective separation and storage of CO2 before combustion. Post-combustion capture methods. Solvent-based CO2 capture. Solvent absorption extracts CO2 from fuel gases by chemical or physical means, commonly used in power plants. Membrane separation. Membranes selectively filter CO2 from fuel gases, offering efficient and scalable post-combustion capture solutions. Adsorption techniques. Adsorption uses solid materials to capture CO2 from emissions, enabling regeneration and reuse of adsorbents. Direct air capture and emerging innovations. Direct air capture technology. Technology captures CO2 directly from ambient air, enabling reduction of greenhouse gases effectively. Emerging innovations. Innovations include enhanced materials and optimized processes, improving capture efficiency and scalability. Geological storage and sequestration, CO2 injection process. CO2 is injected deep underground into rock formations to reduce atmospheric emissions effectively. Suitable storage sites. Depleted oil and gas fields or saline aquifers serve as secure storage sites for CO2. Long-term sequestration. Injected CO2 remains trapped securely for centuries, preventing its release into the atmosphere. Carbon utilization in industry, carbon conversion benefits. Utilizing captured carbon creates valuable products, reducing dependence on fossil fuels and lowering emissions. Product applications. Converted carbon is used in building materials, fuels, and chemicals, supporting sustainable industrial growth. Monitoring and safety of carbon storage, continuous CO2 monitoring. Regular monitoring uses seismic surveys and sensors to ensure CO2 remains safely stored underground. Leakage risk mitigation, regulatory measures and technological tools reduce the risk of CO2 leakage and environmental harm. Ecosystem protection, monitoring protects ecosystems by ensuring carbon storage does not negatively impact surrounding environments. Cost and scalability challenges, high capital costs. Large initial investments are needed, which restrict widespread adoption of carbon capture technologies. Operational expenses, ongoing operational costs contribute significantly, impacting the economic feasibility of large-scale projects. Need for innovation. Innovative technologies and processes are crucial to reduce costs and improve scalability of carbon capture solutions. Economies of scale. Scaling up production and deployment can lower costs, making carbon capture more financially viable globally. Environmental impacts and risks. CO2 leakage risk. CO2 leakage poses environmental hazards and threatens atmospheric balance, requiring stringent monitoring. Ecosystem impact. Local ecosystems may suffer from disturbances caused by capture and storage activities affecting biodiversity. Energy use concerns. Energy-intensive capture processes increase overall carbon footprint, necessitating efficient technologies. Policy frameworks and incentives. Government policies. Government policies provide essential support to encourage adoption of carbon capture technologies worldwide. Carbon pricing. Carbon pricing creates economic incentives for reducing emissions and investing in carbon capture solutions. Subsidies and incentives. Subsidies and financial incentives lower costs and promote investment in carbon capture technologies. Regulatory frameworks. Regulatory frameworks integrate carbon capture into climate action plans and enforce compliance. Integration with renewable energy. Carbon capture benefits. Carbon capture helps reduce emissions, lowering the overall carbon footprint of industrial activities. Renewable energy integration. Renewable energy sources like solar and wind support cleaner production by providing sustainable power. Sustainability enhancement. Combining carbon capture with renewables enhances sustainability through cleaner, more efficient production cycles. Potential for negative emissions. Direct air capture technology. Direct air capture technology extracts CO2 directly from ambient air to reduce greenhouse gases effectively. Pathway to negative emissions. Negative emissions technologies help achieve climate targets by removing more CO2 than emitted globally. Conclusion. Role in climate mitigation. Carbon capture significantly reduces atmospheric CO2, helping mitigate climate change impacts worldwide. Advanced technologies. Innovative technologies enable efficient capture and storage of carbon dioxide from various sources. Economic and policy support. Economic incentives and supportive policies are essential to drive adoption of carbon capture solutions. Thank you.